Problem 1. In the diagram below, the charge on both particles A and C is Q. The charge on particle B is minus Q. The radius of the circle is R, and particle A is at the center of the circle. The angle theta is 60 degrees, and you can leave all answers in terms of K, Q, and R. So, first part is draw a free body diagram for particle A. Alright, particle A. Let's put a dot here representing particle A. Now there are two forces acting on it. One is due to particle B. Particle B is negative. Right? This particle here is negative. And since particle A is positive, it's going to be an attractive force. So let's draw. And that's a very attractive force, I would say. That's force on A due to B. Now the next one is the force on particle A due to particle C. Particle C is, what does it say? Particle C is positive. So that is going to be a repulsive force. Ew. Repulsive. Let's see. And it's the same distance away, and all the magnitudes of the charge are the same, so that guy is going to be the same length, but it's going to be coming up at a different angle. F on A due to C. Now that is a free body diagram, and I pretty much don't need anything else on there. I am going to indicate the angle here. Now let's think about that just for purposes here of understanding the situation. This angle is 60, right? So this line, the extension of this line that would go down in the same direction this way, should in fact point in the direction of C, right? Because C is directly here, and this is the line connecting A and C, and it points up in that direction. So that would indicate that's a 60-degree angle. Since this whole thing from here, let me draw a dotted line here just to consider that dotted line right there. So that, of course, this whole angle from here to here is 180 degrees minus the 60. That leaves 120 there, doesn't it? So let me put that there. That angle phi 120 degrees. Okay, that might be useful later. Alright, now then, let's move on to part B. Determine the magnitude of the net force on particle A. Now there are a couple of different ways to do this. One is by components. So what you would do is draw a coordinate system. Let me push this up here. We're trying to determine the magnitude of the net force. All I really need is the free body diagram, so we can just put that right there. What I could do is create x and y coordinates. I could draw this force. Let's see, this direction. Get this right. So this should be going up this way. And this is FAB, and this is FAC. Now then, I can decompose in components. I could find the x component. This angle right here now is 30 degrees. If you think it through, remember this dotted line right here comes from the particle C direction. This is 180. This is 60. Therefore this is 60, therefore this inside is 30. So I could take the magnitude there and get a negative component there. I could take the positive component, and that would certainly solve that problem using components, okay? So you have a 30-degree angle here, a 60-degree angle here. You have the magnitudes of these forces, because since all the distances are the same, the magnitudes of these forces are actually quite easy. They're K, q squared over r. So let's go back. Let's just check that. So if you look back here, the radius of the circle is r. Each charge has a magnitude q. So that implies that the magnitude of the force, the magnitude, not this direction, just the magnitude, is simply kq squared over r. So that's easy. So now you just have to do your sines and cosines and all that jazz. But what I'm going to do is I'm going to add these like vectors. I'm going to draw a vector diagram, and we'll see there's a simpler way to get this answer. Let me add them head to tail. So let me start off with FAB, and then let me draw FAC. Now what do we know about that? That's roughly the right direction. We know that this magnitude is the same as that magnitude, right? Because both extra charges are the same distance away from the central charge. We also know from this diagram that this angle between the horizontal and the vertical is 60 degrees. Why is that? Because this angle here is 60 degrees, because that's the angle essentially defined in the problem. If you don't believe me, let's look back up here. See, this angle right here is 60 degrees, see? And that's the angle here, 60 degrees. So this is in, opposite angles or whatever, opposite angles on the opposite side of a vertex. So this is 60 degrees here. We already pointed that out. So if this is 60 degrees, these two are the same side. Let me draw, this implies something about the vector sum. The vector sum goes from the beginning to the end. Here's the F net. But by the geometry here, since this is 60 and these two are the same length, and we know that this must form an equilateral triangle, right? Because if you define the lengths of the sides and the angle, that totally specifies the other side. And the only triangle that has two sides the same with a 60-degree angle is an equilateral triangle, which implies immediately that the net force, magnitude of the net force, is also kq squared over r. So without any algebra, without any trig or cosines or sines at all, I'm able to determine the magnitude of that. Now I'll leave that as an exercise for you. If you'd like to, you can go back and determine the x component by taking this. You take this length, you subtract the length of this triangle right here. You take this horizontal component, so it's this magnitude times the sine of 30 degrees. So it's this minus the sine of 30 degrees, and then for the y component you take this times the cosine of 30 degrees. You square both of those and add them, and then take the square root, and you will find that you get this answer. A plastic rod of length L has a net charge Q distributed uniformly along it as shown in the diagram. What is the value of the electric potential at a point P, a distance L from the end? Okay. First step is a diagram of the charge distribution showing infinitesimal charge elements and integration variable. Okay? Alright, so in this case I'm going to draw an x-axis here for my point P, and I'll draw a little rod there. There's my point P. Now the integration variable is going to be x. This is the x-axis. I'll put a little charge element right here, charge dq. It has a length dx. The integration variable, of course, is x, x is the distance from the vertical axis. Note that the sum of dx equals L, and of course the sum of dq equals capital Q. Okay, so that's my representation of it. Let's scroll down here and look at the next part. Now I need an expression for the element's charge dq in terms of the variable. The element's charge is dq. Now because this is a small piece of length dx, it is a fraction which is dx over L of the total rod, right? Since the charge q is uniformly distributed, that will have the same fraction of the total charge on it. This can easily be checked if it's consistent with these two equations right here by taking the integral. We integrate dq, we should get integral of dq dx. Next step will be express the magnitude of the position vector r of the point P relative to the charge element in terms of the integration variable. That's r will be the magnitude of the r vector. Now let me just point out exactly what this r vector is. The r vector points from the position of the charge element to the point P. So it goes from the charge element out to the point P. Okay? That's the vector. Now what is its magnitude? Well, if you think about it in this case, the magnitude is just the length of this vector, right? This length. And as x varies, which I did not put the variation of x. I realized I left something out, which of course you can go back and correct. You can always add points to your explanation afterwards. We went back and added to define the integration variable a little better here. X goes from 0 to L. That's an important piece of information. X goes from 0 out to L because the rod measures a length L. Okay. So if you think about it, x goes out to the charge element, and then r goes from the charge element to point P. That entire distance is of course 2L because the length is L, and if you remember in the description of the problem, the point P is a distance L beyond. So we know that x plus r equals 2L, which tells us that r is equal to 2L minus x. That really makes sense, right? Because this whole distance is 2L, you subtract out x, and then you get the distance of the charge element to the point in question. Of charge. Next part is the expression for the contribution from each charge element to the electric potential at point P. That small contribution is a dV times k dq over r, as it always is. So let's plug in what we had before for dq. That's q dx over L. And the denominator, if you remember, is 2L minus x. So we get k q over L times dx over 2L minus x. Remember, this part is relatively easy. The hard parts really are setting up, what is this supposed to look like, and what is this, what's this look like, and what's this look like. And once you've got those figured out in the first parts, you just kind of plug them in, and you can get this. The next part is when we need to do the integral. This is when we evaluate the total potential by summing up the potential from each of those little pieces. And that is the integral k q dx for L 2L minus x. Okay, we can simplify this a little. We can take a kq. Oh, we need the integral limits. Remember, the rod starts at the origin, that's x equals 0, and it ends at x equals L. So those are the limits. So we have kq over L, which are constants. The integral from 0 to L dx over 2L minus x. Now, to perform this integral, there's a number of different ways you can do it. You can realize that this is just the integral of an inverse. So you know the integral of like 1 over x would be log. To do this, I think you can use something to make it a little bit more obvious called u substitution if you want. You can define u as 2L minus x. Then du is, of course, minus dx. But then the limits change here. So kq over L. When, let's just put that in. So there's a minus du, and then solving for x, you know, you get basically u in the denominator. The tricky part here is the limits. When x is u, I'm sorry, when x is 0, u is 2L, and when x is equal to L, right, u is L. And this, you'll notice, is from a large number to a small number. So we can reverse that and change the sign of this integral. So we get k q over L, integral L to 2L du over u. So that's the painful details on how we do that integral. Let me scroll up here, give myself some room. To continue, we have kq over L. Now the integral of u is log u, which is kq over L times log 2L minus log L. To continue scrolling, and just as I run out of room, I get the final answer. We know that, wait a minute, there's a parenthesis right here to make that obvious. Okay. You know that when you take the log of A minus the log of B, you get the log of A over B. So we divide this by this. The L's will cancel and you just get log 2. So it's kq over L log 2, which is the final answer. Here we have the final problem. An alpha particle made of 2 neutrons and 2 protons enters a region of uniform electric field. The electric field points in the same direction as the initial velocity of the particle. The strength of the electric field is 65 millinewtons per coulomb. The initial velocity of the particle is 1500 meters per second. A. What is the magnitude of the electric force on the alpha particle, and what is the angle between the force vector and the initial velocity vector? Okay. To determine the magnitude of the electric force, you just have to use the following formula, that the electric force magnitude is Q times the magnitude of the electric field, and that's the magnitude of the charge there. In this case, the magnitude of the charge is going to be 2 times E, because neutrons are neutral, protons carry a charge of E, and the electric field is 65 millinewtons per coulomb. So we can just put that in using the value of E from the data sheet. times 65 times 10 to the minus 3 newtons per coulomb. This final answer, which you can verify with your little calculator to 2 sig figs, is 2.1 times 10 to the minus 20 newtons. The angle between the force vector and the initial velocity vector, in this case, remember that the electric field and the force on a positive particle point in the same direction, right? So the electric field points in the same direction as the initial velocity, and therefore the force points in the same direction, therefore the angle is 0. They both point in the same direction. Okay, next part. What is the magnitude of the acceleration of the particle while it is in the region of constant electric field? And what's the direction of this acceleration? Now for this, you can just think about it. The magnitude of the acceleration, we can just use the fundamental relation that the force, since this is the only force on the particle, should be the mass of the particle times acceleration. So the acceleration is simply the force divided by the mass. Now in this case, the mass of the particle is going to be 4 times the mass of the proton. Now the mass of the proton is close to the mass of the neutron. The datasheet shows that the mass of the proton and the mass of the neutron are the same to 3 significant figures. So since we're only doing this problem to 2 significant figures, we're going to just use the proton mass for that. So that means the acceleration then will just be the force which we just calculated, and I'll take my force out to 3 sig figs just for this interim calculation, and divide it by 4 times the mass to 3 sig figs of the proton and neutron. And that answer is 3.1 times 10 to the 6 meters per second squared. Now, since the direction of the force is in the direction of the velocity, we can say the direction equals the direction of velocity. So it's the acceleration is the same direction as the force, of course, and it's in the same direction as the initial velocity. All right, let's move on to C here. What will be its velocity after traveling for 1 millisecond in the region of constant electric field? Give magnitude and direction relative to initial velocity. Okay, so since its acceleration is in the direction of its velocity, it's speeding up. Now, how much does it speed up? Well, since it's experiencing a constant force, it has a constant acceleration. So the change in velocity that it experiences will merely be the acceleration times the delta t, which in this case is 3.11. I'll go to 3 sig figs just for this interim calculation here. 3.11 to the 6 meters per second times a millisecond. This gives us a change in velocity of 3.11 times 10 to the 3 meters per second. So the final velocity then would be the initial plus the change in velocity. The initial velocity, which I forgot, let's go back up here and look what it is. The initial velocity here is 1,500 meters per second, right? So let's go back. 1,500 meters per second. We can put that in. 1,500 meters per second plus this guy, which is 3,110 meters per second. 4,600 meters per second. That's its final speed. The direction of the velocity, again, is in the same direction. It hasn't moved at all. It hasn't changed direction at all, right? Because the acceleration has been in the direction of the velocity, so all it's done is speed up, and it hasn't changed its direction. Okay. The last part here is measuring from the point at which the particle enters the region of constant electric field. How far will the particle travel in 1 meter per second? Okay. There are multiple ways to solve this problem, including applying equations. So you can use, for example, if you remember the equation, the displacement will be the initial velocity times the delta t plus 1/2 its acceleration times delta t squared. So delta t is the time it spends in the region of constant field. And you can use that equation to solve for it. I'm going to plug that in. That's boring, I think, so let me just do a little graphical analysis, which is my favorite thing to do. So here's 0, and here's 1 millisecond. When it enters, it's going this speed, and when it exits, it's going this speed. Right here. So this is its speed. Here's V0, which is 1,500, and its final is 4,600, and it's speeding up at a constant rate. That's indicated by that. So there's a V versus T graph, and we know that the displacement is the area under this curve. The area under this curve can be simply found to be the base, which is 1 millisecond, times the average height of those. So I'll put an extra significant figure here. And this number turns out to be 3.1 meters. Which is the final answer. That's the distance that the particle travels in that 1 millisecond. Now, you can also check it, you can think about, if you want this formula, relate this graphical solution, where I just chose this area under here, to this graphical solution. If you look at this V naught times delta t, V naught is the 1,500, and delta t is this distance. So V naught delta t is actually this area of this rectangle, right? That leaves the area of a triangle. So what's the area of the triangle? This term is actually the area of that triangle. If you think about it, the area of a triangle is 1/2 the base times the height. Well, what's the base? The base will be delta t. Let me just write it down here. The base would be delta t. There's a 1/2 in front. 1/2 base times height. 1/2 base, which is this. And what about the height? The height, if you think about it, it's the change in its velocity. The height is the change in velocity from 1,500 to that. Well, the change in its velocity is just going to be this. If you look back up here, it's a times delta t. So it's 1/2 a delta t squared, which is exactly what we had in the second term of the formula. So the formula really does agree with this graphical evaluation of the area.